Yeah, over to you.
Yeah, okay. Thanks a lot, Suraj, for the introduction and invitation, of course. And of course, the organization is great. Let me start. The plan of the talk is very straightforward. So, I'll be defining a few things uh, which are needed, and then I'll pose the questions we're interested in, and then, of course, I'll talk about some results. So, let me start with some very basic definitions. For our purpose, by S, we mean a closed, connected, oriented surface. What is homeo plus of S? This is the set of
Uh,
all
I
orientation.
I think Tushar says it's not audible.
Can you hear me clearly?
I can hear you,
Okay.
but it's yeah, it's perhaps a little faint. So yeah,
Okay.
it.
Let me then. Okay. How how about now? Is it
Uh,
fine?
yeah, I think now it's better.
Not very good.
Yeah, now it's better. Yes.
Okay. All right. Yeah. Let me start again then. So for our purpose, S would be a closed, connected, oriented surface. By homeo plus of S, we mean the set of all orientation preserving self homeomorphisms of S. Uh, it's very easy to see that under uh, composition of maps as the binary operation, this is a group. And we have a normal subgroup, which is basically the elements in homeo plus, which are isotopic to the identity map. We are calling it as homeo 0 of S. And the most natural thing to do when you have a normal subgroup of a group is to take the quotient. So we call the quotient of these two groups as the mapping class group of a surface S. And so for each G greater than or equal to 0, we have a surjective homomorphism. We're calling it beta G, okay, from homeo plus of Sg to mod Sg. And this has the kernel as homeo 0. So we'll be using this beta G in further definitions. So what are called fiber preserving homeomorphisms? Okay. So suppose you have a covering map P from C to X. Uh, it's called regular if the action of the deck transformation group on each of the fibers of P is transitive. Okay. For our purpose, we will always talk about regular covers from now onwards. So let P from SH to SG. Okay. So I guess I have defined already what is SH. SH means it's a closed, connected, oriented surface of genus H. Okay. So let P from SH to SG be a regular cover of degree K. F in homeo plus of SH is called fiber preserving if whenever we have Px equal to Py, we must have P composed f of x is equal to P composed f of y. Okay. Now you consider all such fiber preserving homeomorphisms, and we are denoting this as S homeo plus P of SH. This is a subgroup of homeo plus of SH. Okay. And now on this, if we apply this beta map, we have a subgroup of the mapping class group, which is called the symmetric mapping class group with respect to the cover P. Okay, S mod PSH. All right. Now, what is called liftable homeomorphism? Suppose you have some F, which is in homeo plus of Sg. This lifts via P if there exists some F tilde in homeo plus of Sh, such that this square commutes. Okay. Now you consider all uh, liftable homeomorphisms. This again is a subgroup, can be checked. And we are denoting this subgroup as L homeo plus P of Sg. Now, the corresponding, if you again apply this beta map, so beta G in this case, you will get a subgroup of the mod Sg. Okay, we are calling this as liftable mapping class group with respect to P. So now we have two subgroups, okay, L mod P SG and S mod P SH. Now, what is the relation? Is there a way to connect these two via this map P? Yes. So before going to that, let me first say why. I mean, this L mod, it's not the whole of all the mod. Okay, so there are some homeomorphisms which doesn't lift. So this is a proper subgroup. So what is an example? So this will be a standard example in our case. So you have genus 3 surface above and genus 2 surface below, and you consider this axis, okay, vertical axis through the middle genus, and you rotate the whole surface along this axis by an angle pi. Okay, so this will induce a covering map, and it will cover genus 2. Now you see under this cover, this say I have drawn a few curves on our surface. So this red curve A, you can see this curve. If you take the pre-image, it's basically this A1 as well as this A2. Okay, so at the homeomorphism level, so from a curve we can get the dent twist along that curve, right? I'm not going to define what is dent twist is, but this is a homeomorphism of the surface which can be defined given any non-separating curve on your surface. So the dent twist along A can be lifted to the dent twist along A1 and dent twist along A2. So A, the dent twist along A, this is a homeomorphism which is liftable. But now you consider this curve B, okay? It can be seen that this curve cannot be lifted under this cover, okay? So uh, if you look closely, this middle curve around the genus, okay, if you project this curve via this cover, this wraps this B two times. Okay, so if you consider the dent twist along B, to in order to have a lift of this B, you should have a, square root of this dent twist, which is not existing by a paper by Rajiv Sarthi and Maclo in 2011. So we have some elements in the mapping class group which are not liftable. All right. So let me come to the relation that I was talking about. So we have these two homeomorphism subgroups, S homeo plus P and L homeo plus P. So we have a short exact sequence which connects these two. So namely, we have a map pi p, which is defined as this, okay, by this formula, that pi p f of x is equal to p composed f on x tilde, where x tilde is an element in the fiber of x. Okay, so this is a homomorphism of groups, and the deck transformation group is the kernel. Okay, and very interestingly, such a I mean, an analogous short exact sequence also exists at the level of mapping classes. Okay, it's a theorem by Birman and Hilden in a paper in 1973. They have shown that there is a short exact sequence from S mod P of SH to L mod P of SG, and again the kernel is basically the image of this under beta H, but this is basically an inclusion. So it's an injective map. So it's isomorphic to deck P. Okay. And moreover, this S mod is the normalizer of the deck transformation group in mod S. This is also a very interesting fact. All right. So now, yeah, let me come to our project. So whatever follows is a joint work with Dr. Nikita Agarwal, Dr. Neeraj Dhanwani, and Dr. Kashyap Rajiv Sarthi. And we have this paper, which is about to appear in Houston Journal of Mathematics. So what are the questions we are interested in this project? The first question that we're interested in, how to characterize elements in L mod. Okay. Can we find some computable criteria for a given mapping class to be liftable. What is the index of L mod in mapping class group? It's known that this is a finite index subgroup, but what is an explicit formula for the index? And finally, how to find a finite generating set for L mod? Okay. Uh, so we know that mapping class group is a finitely presented group. So if L mod is a finite index subgroup, then of course this is also finitely generated. That's known. But again, an explicit finite generating set is a very tricky problem. All right. So in this paper, we consider a very uh, simple map, basically. So what is the map? We have gk. By gk, we mean k times g minus 1 plus 1. Okay. So from sgk to sg, we have this standard regular k-sheeted cover. I'll be showing you in a diagram. What is this? So which is induced by the zk action on sgk generated by a 2 pi by k free rotation of sgk. All right, let me go to the diagram. So we have such a surface, sgk. Okay, in between, at the center, we have one genus, and in each of these petals, we have k many genuses. Okay, now what we do, we rotate this surface by an angle 2 pi by k. In this case, it has 8 petals, so we have 2 pi by 8. Okay, so this one click rotation by an angle 2 pi by 8 will induce this covering map on our SG. Okay, so this is the map we will be considering. All right, and you can see the deck transformation group of this is ZK. Okay, so this is the first result we have. So let me define what is this map psi. This is the symplectic representation of a mapping class group. So if we consider the action of the mapping class group on the homology of the surface, okay, we get this representation of mod in sp2gz. This is called the symplectic representation. And if we just compose this map by the modulo k reduction map from sp2gz to sp2gzk, we get a map from mod sg to sp2gzk. Okay, we are calling this as psi k. Now, we have given a symplectic criterion. So given a mapping class in mod sg, how to check whether it is lying inside L mod. Okay, to do that, you can only check the image of f under your symplectic representation psi. So this will be the form of the matrix. And if you just check that k divides 2I for all I in between 1 and 2g and I not equal to 2, and D22 entry is in ZK cross, that's enough. Okay, it's an if and only if condition. And similarly, at the level of ZK homology, we have this condition. Okay, going from 2 to 3 is not a big deal. Okay, it's very easy consequence. But we also have another characterization of elements in liftable mapping class group. So what we do, we consider this set. Okay, E1 is the vector, the standard basis vector in H1 SGZK. Okay, and you consider all multiples of E1 by elements in ZK cross. So this subset, if you consider the stabilizer of this subset under the action of mod in your homology, this stabilizer is basically our L mod. So we have shown the subgroup L mod as a stabilizer of a subset in the homology. Okay. Okay, let's move on. So how to go about proving this? I'll give a sketch. The first implication, so one implies one if and only if two, is it's fairly easy. So if f is in L mod, this is if and only if it is represented by a homeomorphism capital F, such that the f star at the level of pi 1, okay, preserves the conjugacy class of pk star of pi 1 sgk, okay, which is the kernel of the map phi, which is induced by pk. So this phi is the map from the fundamental group to the deck transformation group. So f star preserves the conjugacy class of pk star of pi 1 sgk. Okay. Now, since zk is abelian, okay, this is equivalent to the condition that f hash, this is the map at the level of homology. Okay. This preserves the kernel at the level of homology. So car phi prime, phi bar is subset of, so f hash of car phi bar is subset of car phi bar, where phi bar is this induced map. All right. And then you use the definition of pk hash at the level of homology to get this curve phi has this form. And then, like at the level of matrices, you just have some computations and you get the form that we have reduced. Now, how to see the condition? So the implication from 1 to 4 and vice versa, the stabilizer one. So this is a sequence of arguments that you have given. Uh, we consider the following series of correspondences. These are all one-one correspondences between finite sets. All of them are finite sets. The first set is you consider all regular k-sheeted covers, pk, from sgk to sg, whose deck transformation group is zk. Okay, we're calling this as ck. Now, this is in one-one correspondence with endomorphisms from so pk star from pi 1 sgk to pi 1 sg, such that pi 1 sg mod this pk star of pi 1 sgk is your deck transformation group. Again, this is in one-one correspondence with all epimorphisms. Okay, right? This we have seen. So pi 1 sg to the deck transformation group, such that the pk star of pi 1 sgk is equal to car phi, and you vary this pk in your ck. Again, at the level of homology, because this zk is abelian, epimorphisms from phi bar to h1 from h1 sg to zk, such that again this pk hash of h1 sgk is car phi bar. You're varying this pk in ck again, and then from here you can see that this is basically you consider all sets of multiples of v, okay, where v is varying. These are primitive elements in your homology, zk homology. So now we have a one-one correspondence between the ck and the last set. Okay. Since mod acts transitively on primitive vectors in h1 sg zk, it follows that it acts transitively on the covers in ck. Okay. From there we have this equality. So you consider the stabilizer of mod sg. So stabilizer in mod sg of pk, this should be equal to the stabilizer of le1, the multiples that we are talking about. Okay, and this is equal to L mod. So we have such a equality. Now, using this symplectic criteria, we have given a series of applications, okay, which we feel are very interesting. Let me quickly go over all these applications. There are 7 applications. Uh, so the first application is very simple. We used basically the matrix manipulations. So for G greater than equal to 1 and K greater than equal to 2, we have L mod PK SG intersection L mod PL SG. This is nothing but L mod PD of SG, where D is this LCM of KL. Okay, intersection of two L mods is again an L mod. All right. The second application is giving us the index of L mod in mod. Uh, So let's call this image of L mod under psi to be IG, and image of L mod under psi k to be IGK. Okay, we have shown that using again the symplectic criteria, that the index of L mod in mod is basically the index of IG in sp2g, and which is again equal to index of IGK in sp2gzk. And from there we have deduced that this is nothing but you compute the primitive elements in your homology, zk homology. You take the number of elements there, and then you divide by the phi k. So phi is the Euler-Toshin function, and in particular, if k is prime, we have this formula. This is the index formula for k prime. The third application is uh, it relates to uh, a result in classical number theory. Uh, so it's classically known that there exist normal series of congruent subgroups in SL2Z. Okay, so these are all congruent subgroups. The definitions are here. Okay, so we have gamma k uh, inside gamma 1k and gamma not k, and these are the definitions of these congruent subgroups. All of these are subsequently normal sitting inside the next one. So we wanted to have an analogous normal series in mapping class group level. So how do we, I mean, how do we get a motivation for this? So here is the motivation. Uh, we note that if you consider mod S1 of K, so this is the level K subgroup. Okay, if you consider the image of this subgroup under your psi, this is basically gamma K. Motivated by this fact, we aim to come up with an analogous normal series in mod. Okay, we define this particular uh, subgroup of your mapping class group, which is basically the stabilizer of this E1 vector. Okay, so L mod, in case of L mod, we had multiples of E1, but in this case, we have the single vector E1, and we take the stabilizer. We are calling this as mod PK SG E1. Now, uh, there is a natural epimorphism from this to ZK cross. Basically, you send the matrix to the D22 entry, and whose kernel is this. So from some calculations, we deduce this normal series in our mapping class group. What is that? So the first group is the level K subgroup. Okay. The second group is mod PKSG E1, and the third, the most bigger group is L mod PKSG. So we have shown that all of them are normal in subsequent groups. And again, the quotient is all again similarly is isomorphic to ZK cross. And moreover, we have uh, some presentation for the elements in this quotient. So if you take the quotient L mod PK with mod PK SGE1, this SK double prime, these elements are the coset representatives. Okay. The fourth application, we have defined the intersection of all L mods to be a group which we are calling universal liftable mapping class group. Okay. So for a fixed G, we consider all L mod PK as G. We are varying this K here. Okay. To take the intersection. First of all, this is a non-empty subgroup, non-trivial subgroup. Why is that? Uh, you see that the totally subgroup, the totally group I of SG, this is sitting inside our level K subgroup. And again, this is sitting inside our L mod for each PK or for each K, right? So the intersection also contains ISG. Hence, this is a non-trivial. It should be non-trivial. Yeah. Uh, Then we have again a symplectic criteria for this particular group. Okay, so you have some f in mod sg. You consider the image of this function, this homeomorphism under the symplectic uh, representation as a matrix, and you check that d2y equal to 0 for I in between 1 and 2g, for I not equal to 2, and d22 can be plus minus 1. So if this condition is satisfied, you can say that f is in your L mod, U mod sg. All right. Fifth application concerns the generating set for L mod. Uh, Licorice gave a set of generators. I'm out of time. Uh, this is given by the standard set of curves, the dent twist along standard set of curves in our surface. Okay. Now, among this LG, we are getting a finite set, which is we are calling SGK. This is basically a generating set for the level K subgroup. But I should mention here, no such explicit finite generating set is known. But we are assuming here that suppose such a finite set of generators exists. I mean, suppose you have got some such finite generating set. We know it's finitely generated, but again, we don't have explicit example. Uh, so that's why this is not very explicit. Whatever generating set we are dealing with here, this is not very explicit. We are working on it to make it more explicit in our ongoing work. So now we have some other groups, and finally we have this generating set. So for gk greater than equal to 2, for L mod pksg, we have such a finite generating set. All of these groups are finite. The sixth result concerns finite order mapping classes. We have shown that uh, for some f in mod sg of finite order, and also if you have the genus of the orbifold, the corresponding orbifold for this f finite order map, if it's positive, then f has a conjugate in mod pksg1. And the second result concerning finite order mapping classes is for gk greater than equal to 2, if you have f in mod sg, this is irreducible and finite order, then f cannot lie in this mod pksg1 and hence not in L mod. The last application concerns pseudo-Anosov elements. So Robert Penner in 1988 gave a construction of some class of pseudo-Anosovs. We have given some particular type of Penner type pseudo-Anosovs. So we are calling an admissible tuple to be like such a tuple, and corresponding such a admissible tuple, we are defining a class of Penner type pseudo-Anosovs. So these any such h tau will give a pseudo-Anosov. Okay. Now, what are the results concerning this? Given any admissible tuple tau of genus G, h tau is pseudo-Anosov. This is the first one. Also, mod Sg is generated by 3G many pseudo-Anosovs of the form h tau. Okay. And given any admissible tuple tau of genus G greater than or equal to 2, h tau is in L mod if and only if k divides L1. What is L1? L1 is the last index. Okay. So if you have j equal to 1, you get this L1. If you just check L1 and see whether k divides L1 or not, you get a condition for h tau to be in L mod. These are some references. Thanks.
Let's thank the speaker. Any quick questions for Soumya? Okay, I have a question, but perhaps I will wait until the break because I'll ask later. Yeah. Okay, let's thank the speaker again.